All right. Welcome, everyone, to the Fuzzing Workshop. I'm Laszlo. I lead Google's fuzzing team, and I'm one of the organizers of this workshop. And I'm really thrilled to have you all here today so we can talk about our favorite topic, fuzzing. First of all, I want to acknowledge and introduce the other organizers of this workshop who have done way more work than I did to make this event possible. Marcel, who got us all started, Rui, who leads our artifact evaluations, Yannick and Rohan, who actually did the vast majority of the organizational work this year, and Vasu, who will be my co-host today. So to give you a little historical background, this is the 5th Fuzzing Workshop. So because fuzzing is essentially in the intersection of security and general software testing, we intentionally try to alternate our co-location between NDSS and ISTA, which is the biggest software testing conference, so that we can reach both of these communities, both the security community and the testing community. We started here at NDSS in 2022, here in San Diego. Then for 3 years, we co-located with ISTA all around the world, Seattle, Vienna, Trondheim. And now we are back in San Diego at NDSS again, so full circle. So what is the Fuzzing Workshop all about? Well, of course, fuzzing, duh. But also, we are the first computer science workshop that implements the so-called pre-registration-based publication process. So in this process, papers are published in 2 stages. Stage 1 publications are basically papers without the experiment results, without the experiments carried out. And these are called the registered reports. And these are the ones that are presented and discussed at this workshop. These papers were solely accepted based on the novelty of their hypothesis and the rigor of the proposed evaluation methodology. And once the authors carry out the proposed experiments in stage 2, they submit their final paper to the ACM TOSM journal, where the full paper gets reviewed again based on the adherence of the agreed upon evaluation methodology. So why do we do this 2-stage process? Why do we need to go through all this extra effort? Well, primarily because it really elevates the scientific rigor. It reduces bias. It prevents, for instance, cherry-picking results, p-hacking, stops harking, which is hypothesizing after the results are known. The early peer review feedback basically ensures that the experimental design is really high quality, and therefore it prevents wasted effort, for instance, doing the wrong experiments. And this process also allows publishing well-conducted research, even if the results are not that exciting, which is great because it can save the community time, because people won't try the same idea over and over again just because the idea never got published. So aside from registered reports, at the workshop we also have short papers, also known as fuzzing nuggets. These are 4-page long evidence-based position papers and experience reports. The purpose of these papers is not to propose a new research idea, but rather to share valuable insight, opinions, reflections on fuzzing from the field. So looking at the numbers for this year's workshop, we have received 31 total submissions. We accepted 10 out of these, which breaks down to 8 registered reports and 2 short papers. Each submission was carefully reviewed by our 30 PC members, some of the best fuzzing experts from institutions across the globe. Without them, none of this would have been possible, of course, so I want to extend a massive thank you to all our incredible PC members for their hard work. All right, so here's our schedule for today. So after this welcome, we'll kick things off with our first keynote. Then after a short break, we dive into our first session, which will have 6 registered report talks. Then after lunch in the afternoon, we will have another keynote. Then we will have an open discussion about the current challenges and opportunities in fuzzing. I hope that all of you will participate in this discussion. And finally, we will have session 2, featuring 4 more talks. And then we end with a brief concluding remarks. We are incredibly lucky to have 2 fantastic keynote speakers today. Mathias from EPFL, who will be speaking about how we can advance from what to fuzz to all the fuzz, just in a few minutes. Then after lunch, we will have Sergey Dekant from Code Intelligence /MPI, who will raise and perhaps answer the question of where the fuzz are we going? I'm really looking forward to an excellent day of talks and discussions, so let's get started. Passing on to Flavio, who will host our first keynoter.
Hello everyone again. My name is Flavio. I'm a professor at RUB. Well, actually half of the paper are from RUB anyway. So, university in Germany, where we have an active community about fuzzing and testing. And it's my pleasure today to introduce our first keynote, Mathias. Payer is an excellent, one of the most important researcher in fuzzing automated testing, professor at EPFL in Switzerland. He conducts fuzzing against whatever you can execute basically, right? From embedded system, virtual machine, custom user space, program, and so on and so forth. And it's a pleasure to introduce him to you today. And I guess now I leave the space.
No, keep talking.
Keep
I'm
talking.
still setting up.
Okay. So while this fuzzing is on device to set up everything, I'm hoping the HDMI will sync up with this Linux system.
I'm your best postdoc advisor as well.
Yeah, he was my postdoc advisor.
No, your best postdoc advisor.
Right. Also the only one, so that's fine. Yeah. You see, if you install Windows, it would be much better.
No, it took like 1 second to connect, right? So I'm not sure, right? It's already here.
Good. I leave the stage to him.
Thank you. Okay, this looks good. Thank you for the lovely introduction, Flavio. Always a pleasure to be introduced by folks I've worked with. It's my great pleasure to be here to talk about from what the fuzz to all the fuzz, or more controversially, to tell you about why general purpose fuzzing is dead. And we're gonna talk about this throughout this talk. It's a bit of a reflection on fuzzing through time. I wanted to give you a bit of a perspective, and especially for those that are newer in the field, maybe give a bit of a reflection, allowing you to kind of think where fuzzing has come from and where it is going. And it's kind of a key transition from random inputs to principled exploration and this community explosion that we've been seeing over the last couple of years, with I think more than 100 research papers accepted just last year. right? So this is insane, the amount of, the pace that fuzzing is going on and the amount of changes that are happening. And we're going to look at this through the lens of history a bit, through these 3 different phases, right? Initially, fuzzing started as a form of like random input mutation where we started like just exploring the target program and became this coverage-guided optimization game that we've been playing for the last 8-9 years, essentially gradually improving exploration and pushing as far as we could. And it's now much more about modeling state, semantics, environment, and not necessarily like the coverage guided anymore, or the focus is no longer on coverage, but more on like the secondary factors that we're sometimes still a bit neglecting. And especially as we're pushing towards these other areas, it makes sense to kind of open up our eyes a bit and go beyond just, hey, what's the next best coverage metric? And I'm gonna guide you through these 3 different stages. And it's kind of the transition that we're going like from the past to the present to hopefully the future, or what I would hope to see the future of fuzzing. And this is a keynote that is supposed to be controversial and inspiring for some future discussions. I'm trying to kind of keep this open and interesting for all of you. We're going to start with the origins of fuzzing. And you know fuzzing, right? You've been looking at this for a while. You've been publishing in this. You've been exploring this. And fuzzing is essentially a form of automated testing, right? You grab your input that you get from somewhere, you run the program, and that's a key distinction to some of the, or many of the other techniques, and you observe if it crashes, right? So you're actually concretely running the program with an input, and if it crashes, you've got a witness. And this is a key benefit of fuzzing, this witness that allows you to do debugging, to do analysis, to like help the developer prove, like compared to static analysis, where you don't know if the bug is actually triggerable or not. With fuzzing, you know that, hey, this input will cause a crash. And then you generate new inputs in a feedback loop until you run out of compute cycles. Right? So essentially, it doesn't give you any guarantees, but it tells you that, hey, if you invest a lot of compute cycles through this random stochastic exploration, you will find something, likely. Right? And this kind of happened by accident in the 90s when the community started looking into black box fuzzing, and started with Barton Miller's classic Unix fuzzing experiments. And as more and more people in the room are born after the 90s or after 2000s, it's always good to give a bit of a reflection on these topics. And essentially, Barton was looking at the telnet connections over a modem, and sometimes the phone line was noisy, right? And injected some bit flips. And this observation kind of led to the issue that, hey, suddenly programs crashed. And the idea here was that based on these random crashes or these random mutations, programs were triggered into kind of unexpected states, right? And these random inputs caused a surprising high amount of crash rates. And with the beginning of this first fuzzing experiments, without any instrumentation, without any kind of feedback, the community discovered that, hey, like the software robustness was greatly overestimated. It was very simple, it was very general, but it's also very, very inefficient, as all the mutations are blind and essentially one-shot approaches, right? You just mutate one bit, one byte, one word, whatever, and you rerun the input and then check if something interesting happens. Now, some of the lessons from these early experiments is that software robustness was heavily overestimated, right? So this was the first revelation that bugs are everywhere. And it's kind of changed the scope of programmers. Before, like your average C programmer would just allocate a buffer of 16 bytes for a username, because nobody would ever have a username that's larger than this, right? It was just common knowledge that people didn't put in adversarial inputs. And these experiments opened up the idea that, hey, any input that can be sent by an attacker may not necessarily be well-formed. Right? So it's kind of an interesting early lesson of this. But after the first large set of bugs, very early to the input of the program, from mostly parsing bugs, we hit diminishing returns after these low-hanging fruit, which then kind of grew into fuzzing over the next 20 years that made heavy use of domain knowledge, right? If you wanted to use fuzzing, you essentially created a fuzzer, you encoded an input grammar, you created specific inputs because exactly of this one-shot approach, right? You had your inputs, you did one single modification, you ran it on the target, and you reran it again and again. So this was this lacking feedback mechanism that really limited the underlying exploration. And we kind of learned that structure in fuzzing really, really matters. And in these first early stages of fuzzing, the structure was actually what was driving fuzzing. And then as a little detour, we had symbolic execution, we had static analysis, we had formal verification, where we spent many, many PhD years and PhD lives to explore alternate approaches of program testing and program exploration. But 10 years, 12 years ago, we had this amazing revolution around gray box fuzzing. And it is all centered around one core area. And I think this whole research area wouldn't be around today without this core revelation. It's kind of the basis and foundation. Right? Again, we have this fuzzing or this fuzz testing image. And now the key idea was we don't need to just run the program, but we can kind of keep a little bit of a map. Right? We can explore and we can remember, hey, what areas of the code have actually executed? How have these areas of the code executed? And then keep track of them. And now, instead of doing this as a one-shot approach, where we essentially have to guess an infinite state space, like was the right amount of mutations, we can now remember that, hey, based on this metric that we have here, we have reached some alternate different input. And this is interesting, right? So it didn't trigger a crash, but the input that we just had, like we achieved some coverage that we haven't seen before. So in addition to this initial set of inputs that are always the same, we can now store these alternate inputs that have reached interesting behavior and can further mutate those. So instead of a one-shot approach, we can now make this an incremental approach where we can do some like gradient descent towards other interesting areas. And that was the key revelation. Well, one of two key revelations. The other one essentially was that EPFL was incredibly easy to use, right? So the focus was on high usability. Whereas with symbolic execution engines, you essentially had to have a PhD in symbolic execution to be able to configure it. Fuzzing, you can teach an undergrad in less than an hour, right? So this interesting balance between black box and white box fuzzing allowed us to explore programs almost automatically, and then we got scalability without having to invest 6 years of your life to learn about symbolic execution. And then there became bugs, and lots of bugs. So EPFL was this transformative moment that introduced edge coverage as a feedback signal, great mutation-based input generation, and kind of made fuzzing an engineering discipline. Right? And so this was roughly around 2013, 2014, where it just exploded. And a couple of years ago, we looked into this and into the lineage of EPFL and other kind of fuzzers, and we kind of drew an analogy to the Cambrian explosion. Right? And if you remember your biology lesson from high school, the Cambrian explosion was like the life was like slowly going on for a couple of 100 million years. And then through a couple of nice triggers that were well-timed, life just exploded on Earth. And the amount of species just exploded like crazy. And we've observed the same in fuzzing. Right? In the span of just a few years, and I'm only doing until 3 years ago, we saw that EPFL actually expanded into hundreds of different fuzzers that kind of inherit some of the key properties of this initial fuzzer, slightly mutating, modifying, adjusting, alternating different aspects, right? So this is this Cambrian explosion of fuzzing where our community started exploring so many different features, so many different aspects of the underlying problem that made this a very, very nice thing to work with. Found tens of thousands or even hundreds of thousands of bugs, but from a research community, we're the research community here, right? It became incredibly difficult to track all the features that have been introduced and to compare these different features. And looking at fuzzing, one of the aspects is like when you're proposing a new system, are you actually making progress? Or have you just slightly skewed the distribution a bit and are just sampling a slightly different distribution and you're not necessarily better? Right? So this is an incredibly hard question to answer. We'll look into a bit later. Over time, the fuzzing community grew. The software engineering community steps up, moved away from symbolic execution, started looking into other angles. Fuzzing frameworks became more modular, and there's all these derivatives, extensions, and so on that were added. Also, an interesting observation: fuzzing actually became an infrastructure. Not just at Google, but at many other places, a lot of systems were continuously being fuzzed. Right? So they were being integrated into the CI/CD pipelines with ongoing tests. New commits were tested, were analyzed. There's large frameworks to fuzz our kernel, to fuzz open source software, but also internally, right? So fuzzing essentially solved an enormous class of problems really, really well. Right? So it was very excellent and gave us a head start at finding many of the bugs that are in the code today. But we're researchers, right? I said this before. What does really matter in fuzzing, and which aspects do really matter? Because like we've now kind of gotten obsessed, or for years we've been obsessed with coverage. And it was all about increasing coverage. And coverage does not necessarily mean bugs, right? And we're not necessarily clear what the relation between coverage and bugs is. And especially in more complex software, a lot of the bugs hide behind state. Right? Even if you have covered a piece of code, you may not have the right state to trigger the underlying bug. For example, in protocols, right? Reaching a given code may be easy, but reaching it with the right state can be quite difficult. Same for environments. For example, JIT miscompilation in browsers or in other very complex software systems. Or semantics, right? For example, for trusted execution environments, trusted applications, where you have different trust boundaries that are interacting with each other, which is making this very, very difficult to go beyond simple coverage, right? So we've kind of explored feedback design and mutation strategy as some of the core challenges that we're looking at. And some of the ongoing research that we're still looking into and the community will have to look into. As an example of this area of research, I want to give you a quick overview of an experiment we did where we compared coverage as a feedback metric. And as you know, right, coverage is necessary to trigger a bug, but it's not sufficient. Right? So you have to execute the underlying code to be able to trigger the bug, but it's not everything, right? You have to actually execute the code with a sufficient amount of diversity, with different states, with different aspects, right? It's making this very, very difficult. The buggy code must be executed to trigger the vulnerability, but it requires the correct trigger. Now, what we wonder is, like, instead of fuzzing all of this code equally, can we kind of push exploration towards likely buggy code and kind of go not just for coverage exploration to maximize coverage, but also to exploitation to focus on particular areas as soon as we have reached them. This kind of spirit helps us in many different areas, such as also for kernel fuzzing. So for exploration, we're trying to expand coverage as much as we can. Then for exploitation, we're trying to hit interesting code areas as much as we can. So we've designed this system where we have this mechanism that first, during exploration, we analyze the seed target distance. We mark all the sanitizer labels as interesting targets, and then calculate the distance, like how close individual basic blocks are to these sanitizer labels, and then keep track and try to push them. As soon as we have found seed inputs that actually hit these target basic blocks, we go into exploitation mode, where we try to mutate those interesting seeds to trigger the underlying vulnerabilities. But it's not about the research work that we did necessarily. The bigger takeaway is that coverage is not just a flat space, but we need to balance between the two aspects. And I think this is one of the key takeaways that you can take from this, right? Coverage is a useful metric that you can look at from different angles and then expand towards certain areas. And in a similar vein, I want to highlight mutation strategies. And we looked into Mendel Fuzz, as we observed that EPFL++ at one point in time disabled the deterministic stage. And if you don't know the details of the deterministic stage, takes a seed, goes through each individual byte, and then applies each mutation operator one after the other. Whereas in a havoc stage, which was the default for quite some time, you combine a bunch of mutation operators, you do those randomly, and then you run them with several mutation operators that are randomly combined. To iterate through a single seed in the deterministic stage, you need millions of executions per seed. Whereas in the havoc stage, you only have a couple of thousand executions. And due to this imbalance, the deterministic stage was deemed as way too expensive. It was too costly to iterate and execute a single seed so many times, right? And one of the issues there was that sometimes the deterministic stage actually gives you a very nice signal, and you want to focus on it. But you don't have the resources to fully explore this deterministic stage. So we looked into a way to target the critical bytes that actually result in interesting behavior, allowing us to revive the deterministic stage. We discovered that in 4 of 23 targets that we looked at the time, fuzzers with the deterministic stage actually performed better. But that's only 4 out of 23, which kind of gives us a signal that sometimes it makes a lot of sense to iterate through each of these targets. But we have to figure out how we can actually use this signal. So we introduced 2 aspects, a fuzz map to reduce the number of seeds that are being sent to the deterministic stage, as in it gives us a quality metric as which seeds should be fuzzed deterministically, and if not, we just go for the havoc stage. And in a second step, for these critical seeds that have the potential to do something nice, we inferred critical bytes to reduce the number of bytes that need to be fuzzed deterministically. So instead of doing every single byte in a long and extensive seed, we focus on a few critical bytes, right? And this then allowed us to do a minimized deterministic stage on a few seeds with a few critical bytes, which then resulted in interesting new bugs. And this has then become the default mode in EPFL++, bringing back the idea of running something in deterministically, if it actually pays off. So again, this is not about the research work that we did, but the idea behind this is that mutation quality is an interesting information problem, and we need to be selective, and we need to figure out what kind of information we need when we want to optimize for different aspects, different types of code, different background, and whatnot. So maybe more globally, improving the signal is possible by tracking some form of state. Right? Path coverage can allow us to disambiguate state. We can look at state variables. There's a lot of research from the community on state variables, state tracking, and kind of inferring additional information. And this gives us insight, or gives the fuzzer insight into higher level state. Data flow is an interesting angle that we haven't really solved yet, right? Keeping track of data flow between variables efficiently is an unsolved open problem. And kind of feedback design is still a core challenge on fuzzing and how to actually push for this, right? How can we explore this in an interesting way? So this is also a call for the research community to potentially continue and figure out how to trade off all of these different values. Another aspect that is dear to my heart is that different bugs require different oracles. So far, we've essentially looked at address sanitizer bugs most of the time, right?
99% of all the fuzzing has been focusing on memory safety. Memory safety bugs are severe, but these are not the only types of bugs that can cause issues. There's concurrency issues, there's type safety, where we do have sanitizers to some extent, thanks to the to all of these different options. But looking beyond what we have sanitizers for, one of the big issues that we'll likely be facing in the next couple of years is how to detect logic bugs. Right? Let's say you have code written in a memory-safe, type-safe language. It can still be buggy, right? How can we detect these logic bugs? How can we go beyond simple sig faults and crashes? And how can we adapt our oracles to all of these different bug types? Right? How can we adjust and explore those interesting logic bugs? How can we infer specifications? What do we need for that, right? And how do we push in into these angles? Oracles essentially tell you when you win, right? I've highlighted a few of the oracles like address sanitizer before, and it's not just one signal. There's crashes that tell you, hey, this is a bug that you need to fix, but there's a lot of silent misbehavior in these logic bugs, different with invariant violations and whatnot. And we have to figure out how we can infer specifications and kind of more general oracles as a big open problem. Now, this also calls for benchmarks. We as a community, we need to develop interesting benchmarks that allow us to test if fuzzers actually achieve these target metrics. And we looked into this a bit in the past, and we observed that essentially, like different research works looked at code coverage or number of crashes or number of bugs that were discovered. This is clearly not an ideal situation. We've seen a bunch of follow-up papers from the community, for example, from Thorsten, from others, Thorsten's group and others, but it's still a somewhat unsolved problem and challenge. Code coverage is very subjective, right? It doesn't tell you how many bugs you find, because the core goal of fuzzing is to find as many bugs as possible. Coverage is nice, right? But it's not the main goal. Crashes are also imprecise, right? At the time, the paper said, oh, we had 50,000 crashes. But maybe these were due to 2 bugs, right? So it was not a very effective metrics. And bugs themselves, they lack ground truth. It doesn't tell you if you found 50 bugs in software A, is this better than finding 10 bugs in software B? It highly depends on how well explored and how the code quality of the different softwares is. So we've optimized in the past fuzzers for metrics that are not aligned with vulnerability discovery, and this is something we'll have to push towards as a community to make this stronger. Now, what we thought of as a stepping step for is that we need a ground truth benchmark that not just that introduces individual bugs, but allows the benchmark to test and measure if bugs are reached, triggered, or detected. Right? And this gives you different kinds of signals and allows us to distinguish the different capabilities that fuzzers have and may have. Right? This is an interesting behavior that maybe some fuzzers are good at reaching certain areas, others are better at triggering. And then you can balance between the two aspects. We tried creating this in a benchmark where we reintroduced old existing bugs and front-ported them and is available as a fuzzing framework. Right? It's been cited a couple of times, used in 45 papers across different communities and whatnot. But we've now been looking at this benchmark for 5 years, and one of the challenges that we are facing is, like, how can we keep the benchmark alive and current? While we've invested and burned a couple of master students' efforts on actually maintaining this, it's a big challenge, right? We cannot get an additional paper out of this, which is a currency that PhD students need to graduate, without actually introducing new big contributions. So as a community, how do we keep these benchmarks alive and current? This would certainly need an overhaul, because some of the more recent fuzzers are starting to struggle to compile these backends. there's also a lot of new bugs that have been introduced, right? Maybe the bugs change. Like we want a benchmark that is also current based on the different bug types, right? So maybe the bug types that we have today in software are different from the bug types that we had 5, 10 years ago, right? So the types of bugs may evolve, and this calls for more work on this. And I don't have a good solution to that, so maybe that's a topic to discuss over the break as well. So we've got a bunch of open gray box challenges that we're still facing here, right? How do we improve feedback for hybrid fuzzing? How do we switch between different feedback mechanisms? Can we do something beyond just looking at a CFG? How do we handle state explosion, path explosion, and get into deep states in a program, just scheduling and resource allocation? And there's been a steady stream of continuous improvement for gray box fuzzing. As I said, it's like 100 papers just over the last year, which also makes this a bit difficult to tease out what has actually been improved and to compare all of these different mechanisms. So as we transition towards the future, I also want to leave you with some of the lessons on gray box fuzzing that we as a community have that I thought are worthwhile, right? Fuzzing itself now is no longer just about coverage. It's not the key metric that's left. Mutation is no longer blind. We can actually bias mutation towards certain areas and actually improve the exploration based on that. Also, feedback generation and statefulness are kind of key now, right? We have a finite amount of resources, and we want to do the best possible with the resources that we have available, which kind of gives us this natural transition to some form of domain-specific fuzzing. And this is likely, and in my opinion, what the future of fuzzing will be like. So let us transition to the future of fuzzing as the next step, right? And like 3-ish years ago, we started developing this trend and observed that we have more and more niches that we need to explore. And fuzzing these niches matter and are key, and we need to adjust fuzzing, where the main contribution may not be in fuzzing itself, but actually in adjusting fuzzing to a certain niche. General purpose fuzzers have hit diminishing returns, right? I don't think we need another 100 papers on general purpose gray box fuzzing, right? The returns are going to be rather minimal. It's also going to be incredibly difficult to compare those. And real world systems are incredibly heterogeneous. Maybe we need to go back to the 90s where we had to customize fuzzing to individual systems, or the early 2000s, as environments matter as much as code. So we have this shift, right? We have this fundamental shift that we're now seeing in the community, that not what inputs matter, but where and how to interact with the system starts to matter much more, right? And this, in my opinion, is one of the big changes that we'll have to look at in the future. And I want to use this theme here to explore 3 fuzzing niches as we go forward. I want to leave you with some of the ideas that we're having in these different niches and how to explore them. The first niche that we've looked at is embedded systems and firmwares. And these are incredibly difficult to work with. You've got limited observability, you've got hardware dependencies on customized chip. It may even be incredibly difficult to just get the underlying firmware, right? And a core challenge here is like, do you want to do emulation? Do you want to do rehosting? Do you want to run on a real device? How do you want to interact between all of these different systems? And like we have an increasing amount of these systems available all around us, right? There's my watch, there's my phone, there's the 5G chip on the system, 10 other, like there's a Bluetooth stack running on the watch, there's the microphone that I'm wearing, there's a whole bunch of other embedded systems that are just floating all around us, right? How do we cover all of those? How do we look at fuzzing from the radio spectrum, from the protocol spectrum? At what layer of abstraction should we address this? How do we manage to extract the underlying state and make this truthful? right? One of the challenges for embedded systems is that, yeah, maybe you're fuzzing it, you're finding thousands of crashes, but are these truthful crashes? Are these real crashes that actually could happen in reality on the real system? And this is still an interesting open area where the contribution is not just in fuzzing itself, but actually understanding this niche better. The second niche I want to hint at is browser fuzzing. And you could also say kernel fuzzing, which is kind of similar in topic, but I use browser fuzzing as the example here. Browsers have a huge attack surface, right? Google Chrome is about 70, 80 million lines of code if you count all the support libraries, right? This is massive. This is insanely big, right? It's a huge code base. There's lots of very rich structured inputs. There's different execution domains. There's different compartments. There's different sandboxes interacting with each other. Deep semantic expectations across all of these different angles. And it's like this large ecosystem, which kind of makes browsers somewhat hostile to fuzzing. Right? You want to have one single library that you can fuzz and target, right? But in this current ecosystems, these browsers are extremely challenging to fuzz. There's a bunch of different compilers. There's a bunch of different ecosystems. There's many different libraries running in parallel. And if you focus a bit on JIT compilers, for example, as used in browsers like Chrome, there's multiple compilers, there's multiple stages, there's de-optimization, there's interactions with system libraries, there's de-speculations, there's different invariants, there's even different languages, right? It's not everything is written in C, C++, but there's also auxiliary languages. And you may be wanting to fuzz complex browser engines, but there's interactions between components, and you're generating code. What does coverage mean in this environment as you're interacting between these two areas, right? You start executing in this interpreter. You may be switching to the just-in-time compiler. When an invariant fails, you go back to the interpreter. You're switching between worldviews and whatnot. Code coverage becomes meaningless in this environment, right? How do you abstract this behavior in such an important but incredibly difficult to analyze environment? So we looked at differential JavaScript engine testing with one of my postdocs that gracefully introduced me, and a few students in the lab, where the idea is that, well, we don't necessarily want to look at code coverage, but maybe we can look at some form of state abstractions and dumping information at specific locations so that we can observe differences between these execution frames from the two different areas, and then kind of through these state differences infer what the potential miscompilations could look like. And this kind of resulted in interesting bugs that we discovered across a very mature pipeline, a very mature system where by comparing these memory dumps of baseline optimized executions, we discovered 8 new bugs in V8. And Liam just shared that this was actually integrated into Google's browser test suite recently to follow on and explore this as we speak. Right? But it's the key message here is how difficult it is to actually go beyond coverage in a system where coverage is no longer a key metric. The third niche I want to talk about and spend a bit more time on is the Android environment. Again, Android has a huge attack surface. Right? The code base is massive. There's, on your average Android, there's a whole bunch of system daemons running. There's lots of different systems interacting with each other. There's also a lot of different privilege domains, right? Code base, again, is huge. There's structured inputs between all of these different components that are communicating. There's trust boundaries that are also challenging to even understand, right? For the average user, Android is just like, I start an app, I run it, I'm good, this is it. But the ecosystem in the background is incredibly complex. right? So if you look at the Android ecosystem, for example, there's the normal world where we have our applications that are running, but we also have this trust zone, this hidden world on the side where we run a bunch of applications. And you may not know the logos of these applications, but this is essentially where all your private data relies, with your fingerprints, your keys, cryptographic keys, your passwords, storage, and whatnot. Right? And these two worlds are communicating with each other, and both of them are running on the same device. Now, an attacker may try to exploit different aspects across this incredibly complex interface. An attacker may be able to install a malicious app, and this is part of the attacker model. The attacker may be able to exploit a bug in an app, or in a trusted application, or even somewhere in the communication between these two sites. And we've started looking across all of these layers of abstractions, and we had to, for many of these systems, we had to adapt fuzzing towards these somewhat hostile areas. You cannot fuzz this large, complex ecosystem in one go. You need to figure out what component you want to look at and then explore and dive down in these components. And this is one of the future interesting targets, in my opinion, that allows us to kind of pick and choose interesting angles. So if you're looking at fuzzing trusted applications, they are used on your phones and follow a common communication pipeline. We started exploring to see if there's actually interesting bugs and vulnerabilities there by building a fuzzing pipeline. We called these T's, where we did some stateful interface fuzzing for these systems, and we kind of leveraged these large and complex system as an advantage. So we started by exploring, given a target trusted applications, we explored all the possible ways how the ecosystem, the normal world, interacted with these applications. This allowed us to understand, hey, these are all the interaction patterns, these are all the API calls that are going into this target. We processed the interfaces and then kind of figured out how the system interacts, recorded some seeds, like this is how the normal world calls into the trusted application, and then used all of this information that we have collected as a fuzzing engine. Right? So the contribution is not necessarily in fuzzing itself, but actually managing these large and complex ecosystem to go beyond what is just a simple fuzzer that we wrote in the end. Communication abstractions are challenging to look at. In the previous world, we used this interface between the normal world and the secure world, which is assumed to be trusted. In this work here, we kind of challenged this assumption, wondered, hey, what's actually happening on this interface layer? I'm gonna tell you a bit about the different abstractions in Android, right? You've got the normal world, as I mentioned before, where your client applications, your rich operating system, your Linux is running, and then the trusted application with the trusted OS, and you've got the secure monitor that orchestrates between the two sides. And through a secure monitor call, you can go from the normal world into the secure world and back. And we wonder that if an attacker that has control over the normal world, if they can actually exploit aspects in the secure world. And it's incredibly difficult to reach the secure world, as you require different levels of abstraction. There's a large complex interface. There's a lot of different just rehosting the target is hard, because there's software missing, there's peripherals missing, and you cannot just grab the secure monitor and boot it up, right? It expects a full Android user land. How do you rehost this? How do you analyze this? Right, it's making this next to impossible. So we did this through 3 major contributions. We used a developer in the loop approach to create a booted snapshot of the secure monitor, then did reflective peripheral modeling, letting the fuzzer figure out what kind of interfaces there are in the system when creating fuzz input, and then derived an interesting fuzzing harness for this. along these three contributions. For the first one, I want to highlight that we actually positioned ourselves that we expect the developer to spend time to set up each secure monitor. And it's kind of controversial in the security community because everything needs to be fully automatic end-to-end, right? But we actually positioned it, hey, like we are investing some developer cycles 1, 2, 3, 4 hours to set up the underlying system. And this allowed us to kind of get a head start. And in fuzzing, this is one of the interesting lessons that I had to learn. We don't want to have everything end-to-end automatic. Like we have to invest developer cycles anyway to triage the bugs, to fix the bugs, and to work with the bugs. It may make sense to invest some developer cycles early on to get much better results downstream. Right? Same as compute cycles, developer cycles are finite. And fuzzing, to me, is like a strategy how to best use the compute cycles and the developer cycles so that we can optimize this and get most of the bugs out of the underlying software. Switching a bit to the normal world, we have not just applications running in the normal world, but also privileged services. And we are seeing in system security a move towards more and more software being rewritten in Rust. And one of the main attack vectors on Android used to be the binder interface, which was the main entry vector into the kernel. And then bugs in binder allowed an attacker to kind of escalate their privileges and gain control over the underlying system. Now, at one point in time, Google rewrote binder in Rust, and this attack vector went away. But what did not go away yet is all the privileged services running in the normal world has much higher privileges than the rest of the system. So targeting these services through the binder interface, so you can use the binder interface actually as a channel to reach these privileged services, remains an interesting target. So these system services are exposed through the binder interface, and as the module is written in Rust, the exploitation can focus on the C++ services without having to escalate to the kernel. We implemented a fuzzer, but again, the contribution is not in fuzzing itself, but the contribution is actually figuring out how to extract the underlying interface, how to kind of demodel and lift the binary information into this system that allowed our fuzzer to generate interesting targets for these systems. So in this study, we targeted on-device system services. We didn't rehost. We were running the native Android system services on the device, got coverage through binary rewriting, but still found interesting behavior through crashes in these systems. Now, some of the open fuzzing challenges as we move on from the niches back towards the future is that the security relevant state is somewhat outside traditional coverage. Right? I've kind of tried to hint at this from the different niches, and there's kind of different angles where and how to target these aspects. So we need to model stateful interactions across trust boundaries, and in Android, I've just shown you like 10 different trust boundaries that, depending on what trust boundary you look at, you find different bugs. And as security researchers, we have to decide which trust boundary we want to look at. How do we abstract this? Is rehosting a good option? Should we run this on device? Can we inject something? How do we alternate between these different modes? How do we model the underlying state? Right? What's this angle here? How can we be aware of the environment to figure out what a good attack vector is? And my take here is that we need to make this implicit state much more explicit, and this is what we're trying in some of our papers to actually highlight what to target and how we can target it. So through the last 40 minutes, I tried to show you how we can go from what to fuzz to where to fuzz, right? We need to decide at what level of abstraction, where we inject our fuzzer, where we inject our abstraction, what kind of coverage metric we want to have, how can we abstract this at the right abstraction level. It's not just control flow graphs, state machines, or system interactions. It kind of depends on each scenario, and I'm arguing for a much more modular approach for fuzzing, where we can look into semantic state environments at the right level. I think this is one of the key messages that I would want to leave you here today. Along with, maybe you would like to join us on this research journey. Right, I'm showing here the picture of the EPFL campus, right next to the lake. We do have a beach as well, with beach access, about 10 minutes from campus. And we're offering postdoc opportunities, PhD opportunities, or interns if you're a PhD student. Right? So you may want to join us on this research journey. And a lot of the research that I presented today is done by the postdocs, the PhD students, the interns that are doing all of this heavy lifting to help explore all of these different interesting areas. So they deserve most of the credit for all of the research work. It's amazing to be working with such a great team of people, and I'm incredibly proud for all the support that I get. And they allow me to spend time on the beach at EPFL, or like on Sunday, actually be on the ski slopes, right? Which may also be interesting for you. So to wrap up, right, we've explored from the origins of fuzzing through the gray box revolution towards fuzzing the future, and kind of looked into the different aspects along the way. And if you look at the origins of fuzzing, fuzzing has now matured as a field, right? It's a well-established research field that has a solid community that is working on interesting problems, on addressing these targets and improving software quality as a whole. Coverage-guided fuzzing over the last 10 years was a massive success and allowed us to explore and push fuzzing to become the most efficient and most effective bug-finding technique that any undergraduate can integrate into their code base. And in my opinion, as we're moving on, the next breakthroughs are going to be contextual and semantic, lifting to the right abstraction and figuring out where you want to fuzz is going to be key. Right? So from what to fuzz to where to fuzz. Thank you very much for your attention. I'm happy to take any questions that you have.
Anyone has some questions for Mathias? We are open. Go ahead.
I have a question. Thank you for the fantastic talk. Yeah, it was really nice to get the historical perspective across the years. One thing you mentioned in the Gray Box Revolution unit was about how to best evaluate fuzzers. You showed the limitations of coverage. You showed that there's no ground truth for bugs. And I think one thing is, yes, we've kind of learned that coverage is not sufficient. But I think also one thing we've done over the past few years may be sort of over-indexing on bugs and new bugs found and things like that. And bugs are very sparse. You could design you can tune various fuzzing algorithms to find different classes of bugs. Yeah. So I'm curious what you think of kind of a push towards more synthetic bug data sets and things like that. If you think that's a step in the right direction, maybe there's also issues with that, obviously. Maybe with LLMs now, they can create better, like deeper bugs than, mutation testing traditionally in the last decade. So just kind of curious to get your thoughts on synthetic bugs and how we kind of solve this bug sparsity problem.
Yep, thank you for the question. Excellent question. I don't have a solution. That's a short answer. But I have an opinion I can share. It's a very, very challenging situation. I think we've tried synthetic benchmarks with Lava, which was the Magma was kind of the successor to Lava, and in the spirit that these artificial bugs are just not good enough, and fuzzers can overfit to these bugs. But then fuzzers can overfit to other types of bugs as well. And it's fuzzing is like this random stochastic process that if you just slightly tune, it will find more bugs, right? And if you compare, like you have software A, and related work A found 50 bugs. These bugs have been fixed. You look at the new version of the software, and you slightly tune. Fuzzer A will no longer find any new bugs because it plateaued, right? But your fuzzer was just skewing the randomness a little bit. You will find bugs, and obviously you're going to be better. But are you really better? Right? It's extremely difficult to evaluate. I don't have a good solution on how to look into this. Maybe LLMs are a good option to look at. Maybe extensive benchmarks. I would hope for like the community to improve the underlying benchmarks. I think the idea of Magma still has merit with the different bug oracles, where you figure out where the bug was and you insert given oracles to if you've reached or triggered underlying bugs. The question is how to select them, right? How to go beyond the memory safety bugs, how to target the logic bugs. Maybe like some automatic approach could help, but it's an extremely challenging question. I don't have a good solution. We're trying to extend Magma, but it's hard. Right? It's very hard to figure out good metrics, and any metric you design will be gamed. That's the logic of metrics. Thank you for the question.
Yeah, thanks.
Oh yeah.
Okay. Thank you, everyone. Nice talk, Mathias. I'm Pascal. I'm PhD student at Purdue. I think one interesting aspect of his talk is that there was no AI up until now. But then I want to ask an AI-related question first. So with the whole increase in large language models and their effectiveness in different areas, what do you think are the most interesting places within the whole fuzzing ecosystems that large language models or AI generally can best be applied to improve fuzzing effectiveness?
Yep. There's a bunch. So the question is essentially where and how to apply large language models in a fuzzing environment. Front end, mid end, and back end is the short answer. Front end input generation is an interesting challenge. Right? Maybe we have plateaued for the given inputs that we have. Asking an LLM to create more interesting input that reaches different coverage is certainly a good target. Harness generation is another one. Right? Let's say we look at the library, libpng, whatnot, creating interesting, better harnesses that go for other API combinations would be interesting. There we can use AI tools. Mid-end, I don't think we should have LLMs in the hot loop because they are just too costly for that. But if we're looking towards the back-end, triaging, crash analysis is definitely another angle, right? We can collect many crashes, merge them, analyze them, and then potentially improve the code. And most importantly, I think patch generation is a very interesting target for me, right? Because fuzzing gives you very precise notion of the underlying bug. Like even if you have, and we explored this in previous work, if you have a given crashing seed, you can actually focus on this crashing seed and make sure it crashes always at the same location while mutating. And this gives you a lot of context of the underlying bug, right? You don't just have one input trigger to trigger the bug, but you've got tens of thousands of inputs to trigger the bug. So you can learn a lot about the bug and the context of the bug. And together with this context that you have learned, you can then guide an LLM to actually write a very efficient patch. If you do this blindly on one single crash, the LLM will just insert a return 0 at the first line of main. But if you give it good context, good information, I think patch generation is a very, very cool target. Thank you.
Thank you.
Hey, I'm Kabilan. So you talked about this future of fuzzing and different niche areas in that. But so let's say you're talking about this V8 engine and how to fuzz the V8 engines and stuff. So V8 engine is like one browser application. So you develop a technique and you develop a fuzzing technique for that V8 engine. Now the problem is there are like a lot of browser engine which follow different architecture and different programming languages and everything. So now you have to rebuild everything for that different application. So how do we abstract this away? And even if we abstract it away, how do we create a feedback mechanism for gray box fuzzer to give a proper feedback to create more valid constructive input?
Yep, thank you very much, Reviewer 2. This was essentially what Reviewer 2 wrote for the dumpling paper. Like you did this for one browser engine. This will not generalize. You have to do extra manual work for the next browsing engine. Yes, that's correct. We did this for one engine. It highly customized towards this engine. But my point is that this was necessary. Right? Otherwise, we would not have been able to find these bugs. So we invested engineering time into targeting this interesting environment, and this engineering time was necessary. As I mentioned during the talk, we have to decide where we insert, how we use our engineering time. Like we use it for triaging, we use it for crash analysis, and we may have to use it for engineering to figure out where to place these hooks to dump interesting state that we can later compare. And if you want to do this on Firefox, in addition to Chrome, we'll have to spend some additional engineering time to actually get this there. It's not a perfect answer, but essentially it boils down to requiring additional engineering effort.
Actually, this is the same review that I got for my paper, so.
I usually, like when I'm reviewing papers, I usually step up and try to fight these reviewers because it can still be worthwhile. Thank you.
We still have a few minutes. If anyone has a question or some comments?
Just from the historical perspective again, I would say the way you described our developments through the gray box revolution was going deeper into the general purpose fuzzer, right? And a lot of advancements were, as you showed in that nice tree diagram, going like on very long paths down AFL, right? And for the fuzzing the future topic, we're kind of expanding the tree horizontally.
Yeah.
I'm curious, like, it's sort of related to the AI question, but generating these auto harnesses is very cheap now. Potentially generating input generators is also cheaper than handcrafting AC Smith, for example. So I'm kind of curious, like, how do you sort of, like, I think partially the reason you've seen such an influx in the number of papers and things like that is because we've expanded the horizontal nature this much, because we're able to do that much more quickly now. So how does the kind of fuzzing community identify the key ideas that are going to maybe generalize a bit better rather than kind of expanding the scope of fuzzing as the general contribution?
Oof. You're asking the hard questions.
That's why you're the keynote speaker.
Yeah. I like where libAFL is going, and I think we need more efforts like this, like so that you can make this much more modular, so that you can reuse existing components. One of the challenges I see for a lot of the fuzzing when we go horizontal is that we have to re-implement the fuzzer again and again and again, right? And we have to re-implement a lot of the components again and again. And this is a lot of unnecessary engineering effort, and requires, like, makes this very hard to compare as well, right? Because each fuzzer essentially stands for itself. And with tools like EPFL, where you can grab individual components and reuse the components, I think that kind of allows us to better compare what improvements they actually made. Not just for this particular domain where it was applied, but across other domains as well. And then if you give back, or if you port this back into the libAFL or whatever it will be source, you can actually better compare. It's similar to the metrics before. It's not a perfect solution, but this is where I would like to see this going. Yeah, I fully agree. Modularization will help. Yeah. Thank you.
Oh, wonderful.
Hey, thanks for the great keynote. I'm Bonnie Dong from Arizona State University. So I have a question that for some systems, some input takes a very long time to take effect on the system. So here, like, how do you and these systems has like very little or maybe no indicator on when this input has finished being processed or when it has take effect on the system. So let's say before it hit the bug oracle, how do you decide how long to wait and like if this input is safe for the system?
Yep. I don't have a solution. It's a hard problem. Any kind of complex system, look at the Linux kernel, for example. Right, fuzzing the Linux kernel, it's even, like I think you're aiming at the embedded systems a bit more, but even the Linux kernel, it's incredibly difficult to fuzz. Each execution takes a lot of time. Each, like you're accumulating state over thousands of iterations. Very, very difficult to decide where and when to stop. Similar to if you have heterogeneous distributed systems, like how do you know if it's settled? Right? For example, we're looking at some protocol fuzzing where we target complex daemons across several processes. Like how do you even collect coverage across these systems? How do you merge them? How do you decide if the system has settled, right, and is not waiting for a timer or whatnot? There's going to be ad hoc solutions, potentially deciding that, hey, there's no timer to wait, the system has settled, you collect some information, but it's going to be very problem and domain specific. And so you'll have to figure out what aspect, what gives you a signal to decide that it's been good enough. Like for general purpose gray box fuzzing, we've just used a timeout. But a timeout can also be incredibly inefficient, especially with distributed systems. So you'll have to figure out a better way to decide. Thank you.
We maybe still have time for a very quick question, or else we can. Still?
Yeah, we have one more.
Oh.
Or, no, I don't know. We have time for
Ah, okay.
Yeah.
Otherwise, I'm happy to be around for the coffee break and any other kind of questions that you have. We're still doing a little bit of fuzzing, much more customization towards different areas. It's been a pleasure to be here, and I look forward to all the ongoing discussions for the rest of the day. Thank you very much, folks.